Hey everybody, Dr. A here, and in this video we're going to be exploring an example of how to use the equivalent lateral force method to determine the seismic design story forces for a building. Now in this video I'm going to be referencing the new ASCE 722 document. I have another video on my YouTube channel where I do basically the same example, but using referencing the ASCE 716 document. So if you're looking for ASCE 716, you'll find that in a different video. This is going to be referencing the brand new ASCE 722. So let's go ahead and get started. We're being asked to use the ELF method, that's the equivalent lateral force method, to determine the seismic design story forces for a two-story special reinforced concrete shear wall office building that is lightly occupied during the week in Memphis, Tennessee. Soil reports indicate that the site has a shear wave velocity of 1,500 feet per second in the top 100 feet of the site. The first story is 14 feet high and the second story is 12 feet high. The story seismic weights are 2,000 kips and 1,400 kips from the bottom up. So maybe pause the video and write all this information down. The other thing you want to do is get out your ASCE 722 document, your books, and follow along in ASCE 722. I'm not going to be showing any screenshots or images from ASCE 722, but I will reference different sections and equations in it, so it would be good if you have yours available so you can follow along and pause the video as you need. So let's go ahead and look at the first part of the solution. I went ahead and I sketched what's called a lump mass system of the situation we have. So we know it's a two-story office building. We don't really know a whole lot of details about the framing or the number of bays that we have. We just know it's two stories, and we know what those seismic weights are at each story. So whenever you don't have very many details in the geometry of your structure, you can just draw it as what's called a lump mass system, which sometimes is called a lollipop model. You just draw a vertical member that represents the height of the building and the different story heights, and then you draw a little circular ball or mass, or in this case weight, that shows the seismic weights at each of the stories, okay, or each of the levels. So we see that the first level here is 14 feet above the ground surface, and its seismic weight is 2,000 kips. And then the second story, which is basically, it's the only other story, its seismic weight is 1,400 kips, and that's 12 feet tall. Okay. Now, if you need to refresh yourself on what a seismic weight is, you want to take a look at ASCE 722 section 12.7. That's actually on page 123 of ASCE 722, and we have the definition of effective seismic weight on that page in that section. I'm not going to go into the details of that. I'm just referring back to what is story effective seismic weight. Okay, so let's keep rolling. The first thing we're going to do is we're going to figure out the soil site class. So I've already done a little bit of this legwork for us. So according to ASCE 722, Table 20.2-1, and this is in the provisions document, if you've got the physical book, we have soil site class C according to this table, and that's because our shear wave velocity was given to us as 1,500 feet per second, okay? The next thing we want to do, which I'm calling step 2, is we want to utilize the ASCE 7 online hazard tool. Okay, so you want to go to ASCE7 hazard tool.online, and you want to do that online. Maybe pause the video now and go ahead and get to that spot online. But what you want to do, and again, I'm not going to show any details of this, I'm just going to tell you what I did. In the standard version, whenever you enter the site, I specify ASCE/SEI 722. I also clicked on Memphis, Tennessee on the map of the U.S. It didn't say exactly where in Memphis we are, so the best you can do is just click and maybe it'll take you downtown. The next thing we want to do is we want to specify the risk category because it does ask us for that. So this is likely going to be a risk category 2 building. Okay. Well, how do I know that? I'm gonna put I'm gonna list that here. Risk category 2. Well, how do I know it's a risk category 2? Well, again, if I refer to ASCE 7-22 and I look in chapter 1 and I'm looking at page 5 in ASCE 7-22, table 1.5-1, very likely I have a risk category 2 building based on it being an office building that's lightly occupied throughout the week. There's no indicator that it's risk category 1, 3, or 4, so I'm going to go with risk category 2 there. And then in the ASCE 7 online hazard tool, I'm going to select soil site class C. I'm going to select the seismic load type, and then I'm going to go to view results. And then if you click the full report option, it'll download a PDF for you. If you click on the details version, then that will give you just kind of an online view of your response spectrum. So I'm just going to sketch real quickly just so we can kind of visualize what's going on. The output of ASCE 7 hazard tool, when you click on the details option, the first plot you see is the multi-period design response spectrum. And of course, you're going to get a graph that looks something like this. This is going to be your spectral acceleration, which is really a percentage of G. It's a percentage of acceleration due to gravity. And then you're going to have the period, which has units of seconds here, okay? And it's going to have some kind of plot that looks a lot like this, okay? And this is called, again, the multi-period design response spectrum. So maybe pause the video and go to this online. I'm going to sketch a few of the values here. The last period here is at 10 seconds that it plotted for us, and it gave us a high point here of, I'm actually looking at it myself on my computer. It has a high point here of 1.13, and that is going to correspond to a period here of 0.1 seconds. So if you recall, a multi-period response spectrum is generated with 22 distinct periods, and you can use linear interpolation to extract values in between discrete points. So again, do this yourself with the ASCE 7 online hazard tool. The other important information that we can jot down here is the following. The hazard tool is going to give us SS, which is 1.32. It's going to give us S1, which is 0.35. It's going to give us SMS, which is 1.25. It'll give us SM1, which is 0.45. It'll also give us SDS, which we may use later if we want to do method 2 of calculating C sub S. That's 0.83. It'll give us SD1, which is 0.3. It gives us the long period immediately, 12 seconds. Okay, that's the long period transition period. And it got some other information there for us as well. But this is the key information that it's going to give you, okay? So, and remember, all these spectral acceleration values are percentages of G, all right? So what do we do next? We're going to scroll on down, and we're going to say the next step is to determine the risk category, the importance factor, and the structural response modification factor. So we're going to say, based on the structure, usage, and occupancy, this is likely risk category 2. We actually determined that already a few minutes ago. ASCE 722 table 1.5-1 says an importance factor of 1.0 should be used. Additionally, when you go to chapter 12 of ASCE 722, you can get a response modification factor R equals 5, and that's based on having a special reinforced concrete shear wall system. Because you don't know for sure if you have a separate gravity load system, you want to use the bearing wall category because, you know, we're going to assume that our shear wall is also going to act as a bearing wall, so that's going to give us R equals 5, okay? okay? So we're going to move on down. And the next thing we're going to do is calculate the approximate fundamental period of our structure. So we're going to be referencing equation 12.8-2 and table 12.8-2. I'm sorry, equation 12.8-8, wrote that wrong. And then table 12.8-2 in ASCE 722, okay? We see that we have this approximate fundamental period here. HN is the total height of your building from the ground all the way to the top, which is 26 feet. And then we're going to use a CT value of 0.02 and an X value of 0.75. We're falling in the all other structures categories. And again, I'm looking in ASCE 722. I'm actually on page 125 right now if you're following along. So we can crank this through and we'll get a period of 0.23 seconds, okay? So what do we do next? Well, we can scroll on down. ASCE 7 online hazard tool gave us the long period already, but we can also determine it from figure 22-12 in our ASCE 7 document. So let me actually just double check that that I'm giving you the right figure designation. If you are using ASCE 7 22. Actually, nope, it's figure 22-14. My apologies. -14. I bet you it was 22-12 in the old ASCE 716. So yeah, 22-14 here, okay? And again, we already got TL as 12 seconds from the online hazard tool, so we're okay with that. So the next thing we're going to do is we're going to return to ASCE 722 section 12.8, and we're going to use method 1 to compute our seismic response coefficient, okay? So how do we compute this? Well, we're going to say C sub S equals, and again, I'm on page 124 of ASCE 722. That's going to be a spectral acceleration times our earthquake importance factor I sub E over that modification factor R, okay? Now, what is SA? Well, again, I'm gonna read to you, I'm in the left column of page 124 of ASCE 722. SA is the design spectral response acceleration parameter defined from section 11.4.5.1 and determined for the period TA that we just calculated. So what we do is we actually enter into this response spectrum that we got from the online hazard tool with the period that we just calculated, okay? With the period that we just calculated. And so what we do is, what do we just calculated as? 0.23, all right? And so what we do is we start around here, 0.23, 0.23, and we move up and we hit the response spectra somewhere on that curve and we move over, okay? So I'll go ahead and tell you I am just quickly doing a visual inspection here, and I'm getting a spectral response acceleration value here that we're going to use of SA is approximately equal to, let's do this, I'm getting it as about, sorry, bear with me. I'm getting it as about 0.87, okay? About 0.87, all right? And so now, again, if you read the fine print, it's not even really fine print. If you just read what ASCE 722 says, back in Chapter 11, it says we could linearly interpolate in between data points to grab that SA value. I'm just quickly looking at it, and it is about 0.87, but if you do a linear interpolation between the 2 points on the ASCE 7 hazard tool, you may get like a slightly different value, but it's right around 0.87. We also want to be careful underneath the definition of those parameters in ASCE 722. It says where equation 1282 is used to determine the period T is less than the period where SA is a maximum, the maximum value of SA shall be used. What that's saying is if you calculate a period that lands you somewhere over here, you need to take SA as this maximum value. Well, that's not what happened to us. We got a period of 0.23, which is to the right of the maximum, so we can just hit our curve and move on over. And again, we get approximately 0.87, all right? So we're ready to substitute values in here. So we're going to say that's 0.87 times our importance factor, I believe was 1.0, divided by that modification factor. I think we got a 5 for that. So we can crank this through and we'll get, let's see what we get. We get about 0.174 as our C sub S value, okay? And again, this is using method 1. This is using method 1 of ASCE 722. Now, the next thing we have to do is we have to check the lower limit of C sub S, okay? Now, ASCE 722 calls this lower bounds of C sub S, and it says this is applicable for both methods. There's a method 1 and a method 2. So if I look at the right column of page 124 of ASCE 722, it says C sub S shall not be less than the following. So I'm going to say C sub S lower limit, okay? And it says C sub S shall not be less than this following equation, 0.044 S ds I sub E, which must be bigger than or equal to 0.01, which is a 1% value, okay? Now, we have SDS from our ASCE 7 hazard tool, so we can say C sub S lower limit is 0.044, and then SDS is 0.83 times I sub E, which is 1. And let's see what we get. 0.044 times 0.83 is 0.0365, which is bigger than this 1%. So we can, check that off. So what this is saying is you can't use a C sub S value that's smaller than this, okay? That's smaller than this calculated value that we just got, okay? Now, ASCE 722 says, in addition, if you have a structure located where S1 is equal to or greater than 0.6, you have an additional lower limit you have to consider, okay? So in our case, S1 was given to us by the hazard tool as 0.35, which is less than 0.6. So I'm going to say no need to check the other lower limit of, and I'm just going to write it here just for your reference, but we don't need to check it. The other lower limit is 0.5 S1 I sub E over R, okay? So we don't need to check that because our S1 value from the ASCE 7 hazard tool was less than 0.6, but if it was bigger than 0.6, we would have to check that, okay? And also confirm that we do not go below this additional lower limit, all right? So what do we do next? Well, now that we have C sub S and we've checked its lower limit, we're ready to compute the seismic base shear and the story forces, okay? So I'm going to do this step 7. The seismic base shear is going to be calculated as the following. We're going to say the seismic base shear is going to be equal to C sub S times the total seismic weight, okay? So we're going to use this C sub S value of 0.174, and then the total weight is the sum of these two seismic weights that we were given here, 1,400 and 2,000 kips, all right? So that's our total seismic weight. Let's scroll on down. It's going to be 1,400 kips plus 2,000 kips equals, and let's punch this through, times 0.174. So this is about 591.6 kips is our seismic base shear. Okay. The next thing, and by the way, this is from equation 12.8-1 of ASCE 722. Next, we're going to get our story forces, okay? So our story forces, F sub x, is equal to CVx times that seismic base shear we just calculated, okay? And this is equation in ASCE 722. This is equation 12.8-12, okay? So what is CVx? CVx looks kind of like a scary equation, but it's not that bad. It's W sub x times H sub x raised to the k power, all divided by the summation as I goes from 1 to n of Wx Hx to the k. All right. And this is from ASCE 722, equation 12.8-13. Both of these equations here are on page 125 of ASCE 722. So what are all of these terms meaning? Well, W sub x is the seismic weight at at level x. I'm sorry, level x. So this subscript x means level x, okay? H sub x is the height up to level x measured from the base level. So basically measured from the ground level, okay? So let's go ahead and kind of collect our values here. W1 was equal to what? If I scroll all the way back up, W1 is the 2,000 pounds. W2 is the 1,400 pounds, okay? So W1, I'm not pounds, I'm sorry, kips, is 2,000 kips. And what is that H1 again? H1 was 14 feet, okay? W2 is your 1,400 kips. And what about H2? Let's go back and look at it. What is H2? Is H2 12 feet? No, be careful. Read that right column on page 125 of ASCE 7. It says it's the height from the base level up to the level you're interested in. So actually, H2 is going to be 26 feet, okay? It's going to be 26 feet. So I'm going to come back here. I'm going to say H2 is 26 feet. Okay, so I'm going to go ahead and calculate this denominator first. I find that calculating the denominator first is pretty helpful. So we're going to say I goes from 1 to 2, and we are going to say, you know, that's W sub x times H sub x raised to the k. I almost forgot, what is K? What is K? I almost forgot that. K is an exponent that's related to the period of the structure, and that's also defined in the right column of page 125. And so it says for structures having a period of 0.5 seconds or less, K is 1. That is the case that we have. If you have a structure that has a period of 2.5 seconds or more, K is 2. And if you have a structure with a period in between 0.5 seconds and 2.5 seconds, you can linearly interpolate. Okay, so again, take a look at page 125 of ASCE 7-22. So this is going to get expanded to be 2,000 kips times 14 feet raised to the first power plus what? Plus 1,400 kips times 26 feet raised to the first power. So I'm going to crank this through, and this is going to be the denominator of that CVx calculation. Okay, so I get 64,400 as that denominator here, okay? Now we need to calculate a CVx for each of our levels. We need a CV1 and a CV2, okay? So CV1 is going to be W1 times H1 raised to the k power all over that denominator that we just calculated, 64,400, all right? So let's go ahead and say that's 2,000 kips times 14 feet to the first power over 64,400. And let's see what we get. Okay, I get 0.435. Okay, you can maybe take that out to a few more decimal places. And then I'm going to calculate a CV2. That's going to be W2H2 to the K over 64,400. And then that's equal to 1,400 kips times 26 feet to the first power over 64,400. Let's see what we get with that. We get 0.565. And if you notice, what happens if you add these two CV values together? If you add these up, you get a total of 1, which is correct. Should add up to 1, okay? So now we're ready to calculate the story forces. So F1 is going to be CV1 times that base shear, okay? So we're going to say 0.435 times the base shear that we calculated a few steps up. That's 591.6 kips. 591.6 kips. And what do we get? 0.435 times 591.6. We get 257.3 kips. And then F2 is CV2 times the base shear. So that's going to be 0.565 times 591.6 kips. So let's see what we get times 591.6. We get 334.3 kips, okay? And so if we wanted to draw a nice little figure, you know, you can either, I'm going to draw it as a lump mass system again, because again, we don't know the explicit geometry of our structure here. So I already forgot what those lengths were. What is it? 14 feet and 12 feet. And so we've got this lateral load here, 257.3 kips. And then we've got this lateral load here, 334.3 kips. And then, you know, at the base, we have this base shear of 591.6 kips. And if you notice, again, these two values add up to be the base shear. So this whole thing is in static equilibrium. Now, from here, you can do all kinds of cool structural analysis procedures. You can make a cut here and do method of sections, and you can get an internal shear force. In this story, we call that a story shear. You could do the same thing here, get an internal shear force here. You can get a moment reaction down here. I mean, if you look at this, this is basically like a cantilever beam just flipped vertically, okay? So, I mean, if you wanted to, you could draw a shear diagram and a moment diagram for this very simplified system, okay? Again, this video is really meant to illustrate how to use the ELF method using ASCE 722 and specifically with method 1 of calculating the C sub S seismic response coefficient value. If you found this video helpful, please hit like and subscribe and be on the lookout for other videos like this. Thanks for watching.